Okay, so this is part 2 where I want to talk a little bit about how to manipulate data. Um, so a couple things to point out. We have two graphs here that illustrate the drop in viscosity across two different bleaching stages. So the first one here, we see viscosity in centipoise, and this is our ozone stage. And then when we get to the first stage of chlorine dioxide, we switch gears and we use an intrinsic viscosity as our method for measuring. Now, one thing I also want to comment on, the data that I'm using to evaluate each stage is discontinuous. It's not the same research paper, so the end here does not correspond to the end over here. All we're looking at is changes across each stage to make decisions. Okay. If we were to, for example, increase our oxidative equivalence in the Z stage based on the optimization we were looking at, what you'd find is you double, let's just say if we doubled our application from 0.25 to 0.5%, we would see a doubling of our viscosity drop here. The result over here would only be a decrease in viscosity of about 3%. And the OXE across the would stay the same. Okay. Then you might conclude that, oh, we had a really significant drop. But without knowing what the actual incoming viscosity is related to that kappa number in that process, all we're doing here is just using it as a comparison for making decisions, not necessarily as a continuity. Okay, so recalculating values to see how the absolute viscosity will turn out won't work in this case. Okay, so you look at these two graphs, it's really kind of hard to tell just looking at them which process has a harsher effect on our pulp, right? So if you look at here, the span is only about 30 points. If you look here, the span is over 200, right? And so if we just look at the chlorine dioxide stage, and you look at the incoming viscosity versus the outgoing, it appears on first glance that you're losing a much more significant viscosity than the amount of kappa drop here, right? So one way to solve this is what we refer to as a normalization. You'll hear us talk a lot about this in other classes. You probably heard about it in 248, where we normalize your results to basis weight. So what I'm going to do here, and if you're interested, I'd be happy to teach you how to do this. We're not expecting this in the class. I just wanted to show all of you that this is a technique that you can use if you're familiar with it. And it's basically a way of, I'm going to relativize the data. If you look here, what I'm doing is I'm normalizing the data against a variable that describes the data set already. So in this case, I'm looking at dynamic viscosity in the ozone stage, and I know what the maximum viscosity is in my data set, and I know that the minimum would be 0, right? And so I can compare the relative change and use that range, max, to come up with a range of viscosities, or a set of data points that is now scaled from 0 to 1. They still have the same relative distance that they had in this data set, but now it's unitless, right? And I can do the same thing for both data sets. So here's that graph of ozone, relativized viscosity. And as you can see, the slope of the line hasn't changed. The regression formula will be different because now you're comparing your kappa number to a relativized viscosity. Okay, but otherwise now it's a unitless quantity. And I can do the same thing for the chlorine dioxide stage. So I do the chlorine dioxide stage, and you can see it looks much different. The scale is quite a bit higher because we're not dropping as viscosities down to 0, because you remember that scale was 0 to about 1500. So now here's the relativized viscosity. Changes the appearance a little bit, but the slope and the linear regression has not changed. Right? So now if I overlay these two plots, it gives you kind of a better visual of what's actually happening. And so if you look here, here's the ozone stage. Now you can see that there's a pretty significant change in viscosity relative to the drop in the D1 stage here. And this supports the conjecture or the statements that we've made in the past, where your chlorine dioxide is a much more selective stage, as well as is a lot less harsher for the same amount of work. Okay. Like I said before, just note that this 0.8 here and 0.8 on this do not equate to the same viscosity. These are relative numbers. It doesn't change your calculations or your data at all, and I will do a quick calculation to show that. Now, if you were to use that curve and then wanted to back calculate it, it would be really easy to plot your relativized viscosity versus your, for example, intrinsic viscosity, and you can see that you can back calculate from there. So I'm going to let's calculate the selectivity. That's an easy one based on those two curves, and I'll show you that nothing has changed. So if you recall, our selectivity that we found originally in the original example for the ozone stage was 1.228, and our selectivity for the chlorine dioxide stage we calculated as 8.664. So I'm going to go through and recalculate based on data from these relativized numbers. So we would have the numerator is still going to be the same, right? We haven't relativized that data. So our outgoing kappa is 16, our incoming kappa is still 20. But what has changed is the denominator. And if you look at the graph and we calculate what our viscosities are from the new graph, our relativized viscosity out the door is 0.4856. Divide that by our incoming viscosity of 0.58. You can divide and multiply, and what you will end up with is 1.228. So all we've done is changed the scale, and the distances between points are still the same. We can do the same thing for chlorine dioxide. Again, the kappa number has not changed in our calculation because we haven't relativized that. But from the graph, we can pull out what the new viscosities are based on the relativized data. And our final viscosity is 0.9158 relativized over 1.01, I'll leave that at that, incoming. Okay. And if you do the math, that is 8.664. So the numbers are the same. Okay? So it just makes it easier to compare results. It's just a technique for visualization. So I hope that helps.